Hello, everybody. This is the 2024 Design Expo presentation for MTU Formula SAE. In our presentation today, we'll be talking about the powertrain capstone, aero capstone, EV capstone, chassis capstone, and our drivetrain integration capstone.
Hello, I'm Miles Sterling, and I started the powertrain capstone this semester for the F25. I was tasked with designing, manufacturing, and validating the intake and exhaust manifolds for a new engine that we are implementing next year. The biggest consideration is making the parts legal for competition. In the right, you can see the image of mandatory restrictor placement. And on the bottom right image is the tire surface envelope that the entire intake system has to be within. For the two manifold designs, I created Pew Matrix to help kind of alleviate the design considerations because the sky is almost the limit. The image on the left is the intake manifold, and the image on the right is the exhaust manifold. Those are both final images. And then I also taught myself how to do CFD analysis on the intake manifold. This is very important because it helps depict the plenum volume as well with the intake runner length and the pulses that are generated from the engine. So for the manufacturing that will be taking place next semester, the fuel rail will be the OEM, and the intake manifold will be made out of carbon fiber layups that were made from 3D printed jigs.
Yep, so I'm Jaden. I did the aero capstone this semester for the F25. So the goal was to improve aero performance by changing where our downforce is located and make it a lot higher, and to also reduce weight and cost. So here's rules compliance. On the right is our keep out zones. On the left is where we can have aero components. Simulation, I use Star CCM from Siemens. So we have a high speed and a low speed simulation and a 2D as well. So starting off, I started on the rear wing. I tried a mini element rear wing and it did not do very well. So I changed it to a 3 element. We currently run a 4 element rear wing, and it did the same as a 4 element rear wing with 3 elements. So that makes it cheaper. I also did some front wing. So our mounts for the front wing were just extra weight and extra space. So I added these end plates on the side shown on the right, which are for mounting and add downforce. And also I changed the end plates of our old front wing to have outwash, which improves our other components. I also changed the nose cone because the nose cone is very important. It's one of the first components to hit the car. So I changed that to support the other components as well. Did the undertray. The undertray for our car currently does not do very well. So that was my main focus this year. So I created a higher downforce undertray. So our downforce change, I added 62% more downforce on the undertray, a little bit on the rear wing, lost a little bit on the rear wing, but overall I got an increase of 8.2% of downforce at 14 meters per second. I am also adding a cornering sim, not just for this year and next year, but also for every FSAE team that we have here at Tech.
Hi, I'm Justin McNeil. I'm going to be covering the EV prototype capstone. So the goal with this project was to continue with creating an FSAE EV prototype, which will help our team get started with EVs, get the team experience designing and manufacturing, get components, and get as much information as we can on FSAE EVs.
My name is Marshall, and one of the big components that we had to get for our tractive system on the car was the power electronics. First part of that was the motor controller. So we determined the HV550 based off of criteria of ease of use, cost, weight, and reliability. And the other big component that propels our system is the motor. So we determined with the MRAX 208 high voltage, operates on 50 to 580 VDC input.
For our battery management system, we went with the Orion BMS2 that gives us the safety protections and all the monitoring capability that we need. And then for our battery choice that we went with, we did not obtain this, but we decided to go with the end-of-pack modules. They're easy to use. A lot of teams use them. They're safe, and they would give us the desired system voltage around 360 volts. Within those modules, then we'd be using the Sony Murata VTC6 cells. They're 18650 cells. They have a 3000 milliamp hour capacity, nominal voltage 3.6, all the normal specs that we'd want. And then continuing with that, the configuration we would run with would be a 360 volt 100 amp. That's about our target. So it's 100 series 7 parallel with those Enerpack modules shown there on the right. The reason we did not purchase them was simply because of a cost.
So I'm Caleb, and we also have Holden for our chassis capstone. So there's 27 pages relevant rules in the FSAE rulebook. These highlight the protection envelopes, tubing, and material, as well as many of the templates we have to follow for the chassis. This is our goals table. So we were tasked with designing a 4130 chromoly space frame tube chassis, and we had to reduce the weight and total tubing length while also increasing the torsional rigidity. So on the left, you can see a final chassis CAD model of our CAD, as well as on the right, you can see the welding fixture that we designed.
So then the design, we had to use FEA in order to optimize the geometry as well as the tube sizes that we were using. And this was done to maximize the torsional stiffness of the chassis while minimizing the weight as much as possible. So this was the setup we used to replicate a torsion test in FEA, as well as the results of the output. We were able to achieve 1900, 750, or 1975 Newton meter per degree torsional stiffness. And we can see how this, and this was our testing of our previous chassis, just to understand how a torsion test is done and get some more data on previous chassis. And this is how we can see it compares to other cars. As you can see, the X21 had significantly higher torsional stiffness, but it also had a much higher weight. So we were able to get back some of that torsional stiffness while reducing the weight.
I'm Robbie. I'm on the drivetrain integration capstone. So we're essentially transitioning from an old engine to a new engine. It's same as the powertrain capstone. Mine is integrating the actual engine into the chassis. So there's a lot of different considerations from mounting points, geometries, different weights, etc. So in terms of basically we need engine and differential expected loads, good rigidity, rules compliance for competition, low cost of team, manufacturability, fair design complexity. So those were the options that were considered. They're all slightly different. And ultimately we chose to go with this one based on its low weight, low cost, and high strength. And then for the differential, kind of integrating that into the rear diff mounts. So for those, there were 4 different concepts considered based on how they can actually get it done. So ultimately we chose to go with concept 2. For the variety of reasons listed. It's also going to include a jacking bar. And then that's a slide of a lot of the work that was done this semester.
Thank you all for reviewing our presentation, and we hope to see you at the Design Expo.